Welcome to the office. We want to take another look at an example of evaluating an integral in which we have to determine which method to use to evaluate the integral. And with this particular example that we're going to look at, I'd like to share with you that I did it wrong the first time. I tried something and I made an algebraic mistake, which led to something that was relatively easy to work through, and I found a reasonable answer. It wasn't overall easy, but it was not the same as what it should have been. But in order to overcome that mistake, right, once I recognized that mistake, I had to take a different approach because the mistake prevented me from being able to move forward with the way I had initially done it. So I went with a different approach. I made a substitution that was different, and I tried to evaluate using that substitution, and I couldn't. So I had to find another approach, which turned out to be similar to the first approach that I took. But I tell you all of this simply to say that it's not that this is an overall difficult integral to evaluate. Rather, sometimes we have to try and then try again. I suspect that many of you would have taken the same approaches that I did, partly because I'm the one teaching you how to take these approaches, but also because the directions that we're given, the method by which we decide how we're going to do things is pretty similar. Right, we're all using the same method here. Of course, I have my own preferences. So what I might encourage us to do is to think about what methods we have. We should start by simplifying the integrand. Simplify this thing if we can. Doesn't look like there's much we can do there for simplification, so we leave it. All right. Are there any obvious use substitutions? No. I would not argue that I can obviously turn it into one of these nice formulas. Oh, that's not quite what I wanted there. We cannot turn it into one of these nice formulas that we have on our integral sheet, basic integral formula. So that's not there. Okay. So we say, all right, is there something different that I could do? We move on into that third step of it's not trigonometric functions, so it's not going to be a trigonometric. It's not a trigonometric integral. There is, let's see, rational function. It's not a rational function. It's looks similar to, but it's not going to be partial fractions. It's not a polynomial times a transcendental, so it's not going to be integration by parts, or at least we suspect not, because it's not the obvious situation. And there's no square roots that would encourage us to perform a trigonometric substitution. So I've run through like our basic approaches, and it doesn't really give us anything. So the next thing to do, if we don't have anything that we want to take, is just to perform some manipulations. And in this case, what we want to do is manipulate by performing a use substitution. Sometimes manipulation is multiplying, separating, whatever we need to do to rewrite it in a different way. And I think for this problem, what we can do is we can rewrite by performing a use substitution. And that use substitution is encouraged by trying to write this as polynomial divided by polynomial. Because if I could recognize this integral as the integral of x to the 1/6 being cubed, right? 1/6 cubed gives me 1/2, and x to the 1/6 being squared, that gives me cube root plus 1. Then I can see I have polynomial divided by polynomial. Now, how did I come up with that? Well, I came up with that because I wanted to try and see if I could find it as a polynomial divided by polynomial. And the only way to get that to happen is to find a common denominator for 1/2 and 1/3, which is 6, that common denominator, and rewrite those as powers of x to the 1/6. All right, so once I can do that, this encourages the use substitution to write it as a quotient of polynomials. So it encourages a use substitution. Let u be equal to x to the 1/6. And that would give us du is equal to 1/6 x to the negative 5/6 dx. And we don't have the x to the negative 5/6, but we can represent that very nicely by du. So making the substitutions we need will help us greatly. Now, I've presented a couple different ways of rewriting things when we're performing a U substitution, and the variations are endless. Some are very nice, some are not. And in this case, I know that this thing is very nice in terms of U. So what I could in fact do is to write du as multiply by 6 to get 6 du is equal to x to the negative 5/6 dx. But then I can also multiply both sides by x to the 5/6 to get 6 times x to the 5/6 du. Write that exponent a little nicer there. Go. Du is equal to dx. And why is that nice? Well, because x to the 5/6 is x to the 1/6 being raised to the 5th power. So I can observe this as 6u to the 5th power du is equal to dx. So sometimes you can rewrite things really nicely in that way. Is it always the case? Not always, but there's a variety of approaches that you can take. Some you might be more familiar with than others, and I'm trying to just share a variety. So that way you can use whatever you're most comfortable with. But this, identifying this and this really nicely gives us that this is the integral of u cubed divided by u squared plus 1. And then dx is simply 6u to the 5th u. And that's very nice. That makes the substitution very straightforward. So this is good so far, but what I want to recognize is I can pull out that 6 completely, and then I have u cubed times u to the 5th gives me u to the 8th divided by u squared plus 1 du. And you might say to yourself, does that really help? Right? We've manipulated and we simplified. We performed the substitution and we simplified. Simplification, that's always the first step when trying to evaluate an integral. Here's our new integral. How do we evaluate it? Simplify. But now we have that simplified form and we say to ourselves, what do we do now? Well, it's polynomial divided by polynomial. So this is definitely going to direct us towards partial fractions if that's the case. Now, you might notice that the denominator cannot be factored, so it's really not going to give us partial fractions. But what it will do, or what we can do, is anytime we have polynomial divided by polynomial and the numerator has a higher degree than the denominator, we can certainly perform that division so that way we end up with a polynomial plus a rational function. And then we can work with that slightly simplified rational function. Right, integrating a polynomial, easy peasy, lemon squeezy. So all that we want to do is to find what this quotient is. So the polynomial in the numerator is just x to the 8th power. But we want to recognize that that's plus 0x to the 7th, plus 0x to the 6th, plus 0x to the 5th, plus 0x to the 4th, plus 0x cubed, plus 0x squared, plus 0x plus 0. Why do I want to recognize that? Because when I'm performing polynomial division, I need all of the terms, all of them. And I'm dividing by x squared plus 1. Now I used x here. I should have used u because that's the variable we're working with. So I apologize. I'm not going to change it. All right. So I'm taking this polynomial and dividing it by that one. When I'm performing polynomial division, if you need more instruction on this, feel free to refer to, let's see, that would be any video on polynomial division. Synthetic division doesn't quite work here. You could adapt it, but you'd need a substitution. So we would do, how many times does x squared go into x to the 8th? Well, it goes in x to the 6th times. And that's going to give us minus x to the 8th plus x to the 6th plus 0x to the 7th. So when I perform that subtraction, this minus that goes away. This minus that gives me a negative x to the 6th. And I still have plus all of these zeros. So how many times does x squared go into negative x to the 6th? Well, negative x to the 4th times. So I'm going to subtract negative x to the 4th minus x, x to the 6th minus x to the 4th. So where am I getting these terms? Well, what I'm doing is this one, x squared plus 1 times x to the 6th gives me the x to the 8th that I'm looking for, x to the 6th times x squared. And then I need to distribute to the 1 as well. 1 times x to the 6th is just x to the 6th. And actually, maybe we want to line these terms up. So minus x to the 4th. There we go. So negative x to the 4th times x squared gives me the negative x to the 6th. So when I perform the subtraction, it goes away. And then negative x to the 4th times 1 is just negative x to the 4th. Perform the subtraction. Let's see here, 0 minus a negative is a positive x to the 4th. So how many times does x squared go into x to the 4th? Well, a positive x squared times. So this is going to give me minus some new polynomial. X squared times x squared is x to the 4th. X squared times 1 is x squared. So 0, well, x to the 4th minus x to the 4th is 0. That goes away. That's what we're looking for. And 0x squared minus 1x squared is a negative x squared. How many times does x squared go into negative x squared? Well, negative 1 time. So negative 1 times x squared is a negative x squared. Negative 1 times 1 is a negative 1. For subtracting this to find this minus that goes away. 0 minus negative 1 is a positive 1. All right, so what does that give us? Well, that gives us the quotient as well as the remainder. So by finding those things, I'm able to observe that this is 6 times the integral of x to the 6th, except I don't want x, right? These were supposed to be u's. U to the 6th minus u to the 4th plus u squared minus 1. And then plus the remainder, right? But how do I express a remainder? It's plus that remainder divided by still the u squared plus 1. So this is fantastic. This is actually really nice. 1 over u squared plus 1, that is exactly our formula down here. 1 over u squared plus 1. So this is arctangent. So this gives us 6 times integral of u to the 6th is 1/7 u to the 7th. Integral of u to the 4th is 1/5 u to the 5th. Integral of u squared is 1/3 u cubed. Integral of 1 is just u. Integral, put dx there, that's supposed to be. All right, integral of 1 is u. Integral of this is, again, that's explicitly the arctangent. So this is plus arctangent of u. Don't forget the plus c. But this originally was in terms of x, so we want to let u be x to the 1/6 to get our original variable back. So 6 times 1/7 x to the 7/6 minus 1/5 x to the 5/6 plus 1/3 x to the 3/6 minus x to the 1/6 plus arctangent of x to the 1/6 plus c. And that is what we're looking for. That's quite a bit there, but that's not horrible, right? The difficult part of that might be recognizing that we need to perform the polynomial division and then actually finding the value of that polynomial division. Okay? So you may need to review to be able to follow that a little bit better. But that's all that I have for that example. So we've got another example to look at. So I would encourage you to come on back and visit me one more time for a little bit shorter example on evaluating an integral where the method is not given to us. I'll see you guys again a little bit later.